All right, so I am a Cal Poly grad, second class from the new master's program out there, and I will be talking about prescriptive and performance-based application to a campus media and technology building. So my presentation outline is going to go over the building description, key building features, which makes it a unique building, the fire protection systems associated with the campus building, and performance-based analysis using STEPS and FDS. This is a general site plan of a portion of the campus. The building I'm modeling and doing analysis on is the green building, media and technology, and it's just to note that it's prescriptively compliant with all of the fire department connections and fire hydrants with the university. So it's a three-story performance three-story building with a performance viewing balcony, which is in the section below. The highest occupied floor is 30 feet from grade. The largest floor area is 12,500 square feet, which is actually the second level. It's a mixed-use configuration with Group A and Group B, and is of Type 2B construction. So the principal operations of the building is a campus radio station. So there's a performance studio, telecommunication studios, multiple control rooms, computer labs, and an open office or open offices. So there's Group A and Group B occupancies, which will be separate with rated separation. You can see here is the performance studio below, and this is the viewing balcony, which is actually enclosed, which is not prescriptively compliant by the building code, but was DSA approved space because this is where recording is happening, and they didn't want interference with the sound for people viewing on level 1.5. There's a two-story atrium connection seen right here of the open office. CBC allows two-story atrium connections, but this is a little further complicated by an open stair seen here. It's considered a non-ingress stair, but it connects to 3 levels, basically coming up here and then introducing to the second story and the atrium connection. However, a rated separation was used using CBC section 708.2, using draft curtain or smoke curtain and closely spaced sprinklers to create the 1-hour separation. So this is a clear view of the volume of air as the one space. So here's the open stair, and then the two-level atrium connection. This is the extent of the atrium based where the smoke curtain is and the closely spaced sprinklers. And I'll be talking about the design fire 1, where it's directly below the atrium. In my master's report, I also did multiple design fire scenarios, but we're not going to talk about that today. So for steps analysis, I did occupant loading based on the types of use. So the beige is the office type area and loading, 1 to 100, and then the performance-based locations more as assembly unconcentrated. Areas to note are the exits. The dark brown are the stair enclosures, B and C, and the direct access to the exterior are A and E. Also to note, there's direct access from individual rooms, which are not included in the egress capacity, and stair C is only accessed from levels above. There's no direct access from level 1. Level 1.5 is only the viewing balcony, and all occupants are using stair C. They're not allowed to egress through the open stair. Level 2, continuous open floor plan, mostly office, and only access to the stair enclosures. And then level 3, again, also open office with the 2 stair enclosures. So separation strategy for all buildings less than 4 feet or 4 stories. Exit enclosures are 1 hour, the same for shaft enclosures, and then separation for a data center, which is on level 1 right here, and then the group separation, as I mentioned earlier. The total occupant load for level 1 is approximately 200 people, with a total egress capacity of the 3 exits, main exit, stair enclosure, and back exit of 850 is the capacity. And then again, just to verify that all occupants have sufficient capacity to egress throughout the building are seen in the table. Same for level 2, 187 occupants, and using the 2 egress stairs. Same for level 3. So DSA requires, and the City Code requires, that sprinklers are required for the building. It's considered light hazard, and then the combination sprinkler standpipes in the stair, and then alternative suppression was used for the data center. Fire alarm detection is also required by code, and campus requires a public address system for emergency evacuation for all public areas. And it's also important to note that the soundproof enclosures, because of the recording studio, all visible notification appliances were installed, and then the components. So steps analysis was conducted, basically a brief outline as seen above. The travel speed is based on the type of walking surface and the individual specified, as well as the travel speed is reduced by queuing and or crowding. So the demographics affecting this are age, mobility, and then patient's parameter, which is their commitment to stay to an exit, which was just discussed before. So 2 scenarios were run where the only exits were available were the 2 stair enclosures, and the third option is if people decided to use the open stair, even though it's not in the analysis for capacity and hand calculations. The scenario 1 was, it took about 2.2 minutes for all occupants to egress, and 1.5 minutes for all uses of all stairs. We saw a lot of queuing on level 2 at the stair enclosures, which is typical, and again, which caused more of a problem was using the second egress stair for the direct access from level 1 to the exterior. Occupants would go through that where the stair had converging occupant loads. FDS was also used, so this is the tenability criteria that I used, using the SFPA handbook and NFPA 130, visibility 6 meters, temperature of 60. So a workstation fire was used directly beneath the atrium, and it was assumed to be a sprinkler-controlled fire. So I used the worst case scenario, maximum spacing of 15 feet between 4 sprinklers, using a medium T-squared fire with a height about approximately 29 feet for a total heat release rate of 2,700 kilowatts. The reaction I used was about 50% wood and plastic, with a soot yield of 0.1 and a CO yield of 0.04. So these are the results. The black represents all locations where it exceeds the attainable allowable criteria specified earlier. Visibility fails approximately at 160 seconds on level 3, and temperature fails approximately at 360 seconds, where CO was not an issue for tenable conditions. And level 2, visibility fails later at 360 seconds, and temperature fails at 620 seconds. So I also conducted, to compile everything together, ASET versus RSET. I also did hand calculations using the SFPE method and Paul's method, which is seen in the table on the right, and the total evacuation of steps compiled together in these tables. So the time to alarm was determined to be 45 seconds because it's a normally occupied area and people are familiar with the area. So assume that occupants would, have pull the manual pull stations. However, if this was not the case, detectors would activate 130 seconds, which is the additional end in orange. The pre-movement time was assumed to be 60 seconds based on Perlot's chapter in the SFP handbook for mid-rise office building for occupants familiar with their surroundings. So this just shows that for majority of the scenarios, if it's dependent on alarm, that the occupants would not have enough time to egress in tenable conditions. So further analysis was used to see if phased evacuation would be beneficial for this scenario. Same pre-movement time, same time to alarm. It's just analysis was done per the different egress times using the SFPE method. And we can see here that in all conditions, if it's manually, alarm is manually initiated, all occupants will have tenable conditions, the amount of time to egress in tenable conditions. However, if it's dependent on alarm, level 3 occupants will have reduced visibility in the egress, but they're not affected by temperature. So if it's the building is based on performance design, these would be my recommendations. Excuse me. Phased evacuation using the public address system that's already going to be installed. Regular training and drills annually or biannually for the occupants. Reduce the material but keep track better of materials and have lower soot yields, and minimize the number of workstations and orientation of the workstations below, and possibly not have them right directly below the atrium. And then monitor the amount of combustible material. Alternatives would be enclosing the stair to use it as a means of egress, and or install smoke control system, which is highly unlikely because it's so expensive. In summary, it's interesting to know that the building is prescriptively compliant. However, if performance-based design was applied, it would not meet the criteria. So its SFP handbook states it very well that prescriptive-based design is intended to have a safe building where safe is not clearly defined. And performance-based design is intended to show how a building will perform during the event of a fire. And as fire protection engineers and consultants, it's important to be aware of the difference and to clarify between the client, the owner, and the architect the potential risks associated with these types of decisions.
Thank you. Do you have questions for the speaker? I'm impressed how well all of the speakers are communicating. We have no ambiguity, no questions. That's great. Okay, then thank you very much. We'll move on. Oh, do you have? Okay.
Are you looking to do these types of analysis on other building types? Because obviously that's a pretty important conclusion you came up with there. It would be really valuable if you did the same type of analysis on totally different occupancies. Because if I've understood what you said there, is that the building passed the prescriptive codes, but would have largely been deemed to be unsafe unless specific actions were taken through a performance-based analysis.
Right. So the only reason this was conducted was because of the school requirements of the different analysis need to be done. Like, it would typically have been done based on clients' recommendations. Yeah. So this is why it's important to note, because most clients will say, it's going to cost me a lot more money to do an FDS analysis or a STEPS analysis. Why am I going to do it if it's prescriptively compliant? But if in areas where it's more negative, I guess it's always negative, but in the case of the university, life safety is very important. They don't want anything happening to their students, and it could be on more and more negative connotations. So it's just to be aware that, even though if it's unique geometry, it might not be compliant even or considered deemed safe by performance design
Right.
based on prescriptive.
Right.
Just to follow up, so now that you've done this analysis, what happened to it? The university knows about this? Are they going to take some action, or what's happening? I'm just curious.
It's not actually built. It was in design stage.
Ah, okay.
So I just had the floor plans. I actually don't know what has happened to the building. I know it was stopped by the time that I'd done the analysis. So I don't think it's actually being built, which is what it is.
Okay. Okay, great, thanks.
Anyone else? Yes.
Yes, it's as piece of works. Then I'd like to know whether you all will propose a smoke control system for that building.
It was not feasible. Well, this was just an analysis done for university work. But in my recommendations, further analysis could be to add smoke control, but the cost associated with the building, with the smoke control that could be required, would exceed the, budget or whatever, because it's a campus building. I'm not sure what the restrictions were. And for the amount of space required for the smoke control system, I'm not sure.
Okay, thank you.
Okay. Well, thank you very much. That was great.